We now want to do a detailed analysis of time travel and try and understand some of the paradoxes that are sometimes associated with it. We're going to imagine that Ulysses goes on a journey to a distant place, which we'll call P, at a relativistic speed, and Homer stays behind on Earth. We'll imagine that the acceleration periods are negligibly small in time, whether from Homer's perspective or Ulysses' perspective. So that's kind of unrealistic, but it'll get us to the heart of the matter without too much complication. So what we expect to happen is that Ulysses comes back younger because he's gone off on this relativistic trip, and Homer has seen his clocks slow down. So he comes back younger. The difficulty arises when you reverse that argument using symmetry and say that from the point of view of Ulysses, Homer went on a journey, and therefore, from the point of view of Ulysses, Homer's clocks slowed down, and therefore he should be younger. So we seem to have a paradox. What's going on? Who's younger? Well, just to get to the answer, before we do all the hard work, first of all, the experiments have been done, and we know that Ulysses, the one who went on the trip, is the younger. And the reason is that only Ulysses experienced acceleration. Only Ulysses felt the inertial forces associated with acceleration. Homer never felt anything. So there actually isn't a symmetry between Homer and Ulysses, because Ulysses felt acceleration and Homer didn't. Now that may not seem very satisfying, but let's think of it in terms of length contraction. What happened when Ulysses accelerated was that the distance from Earth to the place P length contracted. If it was a very brief acceleration, it length contracted a lot, all of a sudden. And then Ulysses measures the distance he has to travel in his spaceship as having decreased enormously. So of course it's going to take him less time and he won't age as much as he might have thought. Homer, on the other hand, sees no such thing. Homer didn't accelerate. He doesn't see any change in the distance. He just sees Ulysses in his spacecraft take off. So the acceleration has done something. It has made the journey shorter for Ulysses. Homer didn't accelerate, so nothing happened. So he can't expect the time for the journey to decrease. Only Ulysses can. So we see straight away that there is in fact a physical asymmetry between Ulysses who accelerates and Homer doesn't. But what we're going to do is analyze this in terms of the time elapsed alone, so that we can understand what happens to the clocks during this process. So it's going to be a little bit complicated, so we have to set up a few definitions. There's a systematic way of solving relativistic problems, and that is to first of all identify the frames of reference that are important. And here they are: the Earth frame of reference, S, the rocket frame of reference going outwards, and the rocket frame of reference coming back with the same speed but opposite sign of the velocity. So we've got 3 frames of reference. The second thing we identify is what are the key events that are going on. Well, I've claimed that it's acceleration that's important here, and it turns out that it's the acceleration involved in the turnaround at destination place P to get back to Earth that accounts for the difference in aging. So we're going to focus our events on O, which is the turnaround time, the acceleration from going outwards away from Earth to accelerating backwards towards Earth. And we'll see what that does to the time, and we'll find that it accounts for the difference in aging. So the events we're going to look at are immediately before the turnaround acceleration and immediately after the turnaround acceleration. They will have these coordinates plus or minus some epsilons, which we won't be concerned about, as you'll see. We'll call the time that it takes in the rocket, the proper time for the outward trip, t on 2. And similarly, for the backward trip, it's going to take the same time, t on 2. That means t, capital T, is the total round trip time. So what we're going to look at is what happens to the time on Earth, as measured by clocks on Earth, when the rocket changes frames from the outward growing S' frame to the returning S" frame. Now when we say what happens to Earth time, we mean from the point of view of Ulysses, because we know that Ulysses' first thought is that the clocks on Earth slow down, and so Homer shouldn't age as much. But something else must be going on to account for the experimental facts. So we're asking what happens to the Earth time clocks as measured by Ulysses when he changes frames from outward going to inward going. And to do that, we will use the inverse Lorentz transformations. So as you can see, the two frames are oriented in the same direction, so that positive x is towards the place P, the destination place. And therefore, if we choose our coordinate origin to be at P, the Earth will have the same position in each of those coordinate systems. In fact, the coordinate will just be the velocity of the rocket times the one-way trip time t on 2. And that accounts for all the length contraction effects and so on. That is just the coordinate of the Earth in each of those frames at the turnaround time t dash equals t double dash equals 0, which is what we're calling the origin time. Now we use the inverse Lorentz transformations. The t dash times and the t double dash times are all 0, so when we use the inverse Lorentz transformation for time, we only have the spatial part, and we've just calculated what that is, with the minus sign coming from the fact that the Earth is in the negative direction relative to the orientation of our coordinate systems. After the turnaround, which is from the point of view of the s double dash frame returning, except now the velocity has changed sign to minus v. That's the whole point of the acceleration event. So consequently, that minus sign cancels with the minus sign of the coordinate to give us a plus sign. And the difference between those two times is equal to this expression. That is a time that is proportional to the total trip time t. The time on Earth has jumped from this negative value to this positive value in whatever small time the turnaround acceleration took. So the Earth clock has jumped forward in time a large amount proportional to the trip time. And that is what accounts for the aging of Homer relative to Ulysses. It's a change in frame. And it ultimately comes from the relativity of simultaneity, as you can see from the nature of the inverse Lorentz transformation. We can just verify that. We were originally a bit concerned because we thought that the time elapsed on Earth for Homer would be time dilated, so that it would be less total time, and Homer would have aged less. So that's the blue term. What we've just discovered is that because of the acceleration turnaround, there's a jump in time of the Earth clocks, of the value given there, and do a little bit of algebra on that, and you find that the time experienced on the spacecraft for the total trip increased by the gamma factor. The paradox arose because we didn't account for the relativity of simultaneity associated with the change in frames when Ulysses turned around and came back to Earth. Once we do that, we get a jump of the time on Earth as a result of that acceleration, and we find that Homer indeed aged more than Ulysses. Now that can be understood in a different way, using what's called a space-time diagram, where we have time on the vertical axis and space on the horizontal axis. And what this diagram shows are clocks on Earth, the reading on clocks on Earth. Here is Earth, and time is marching forward for Homer as he stands on Earth, going from -2 units to 2 units. Also shown in the diagram are clocks which are synchronized in the Earth frame, but located at the place P that the rocket ship was turning around at. So the XT frame is here the inertial frame of the Earth, and you can see that the clocks are synchronized as they should be in that frame. If we now go to the outward Ulysses frame, that's the X dash axis here. And in Ulysses frame, we know that the time on Earth depends on the location in Ulysses frame according to that expression. So you can see that time is linearly related to x dash, which is why we draw the x dash axis at an angle. And what we see is that a clock reading 0 at the turnaround event reads -1 at Earth when they're judged to be simultaneous in the S dash frame. Similarly, when Ulysses travels back to Earth, his synchronous clocks, according to his frame, are on that line, as given by the inverse Lorentz transformation, and he then judges the clock on Earth to read 1 unit of time when it's simultaneous with the clock reading 0 units of time at P. So in jumping from outward going to inward going, the reading of the clocks on Earth that are simultaneous with the reading of 0 at P jumps from -1 unit to 1 unit. So that's just the same argument as before, but put in terms of a space-time diagram, and asking which time on Earth clocks is simultaneous with the turnaround time 0 at place P. And the answer depends on whether you're in the outward going or inward going frame. And so as you accelerate from one to the other, what you measure to be simultaneous on Earth changes from a time in the past to a time in the future. The message of this story is just that when you get paradoxes in relativity, it's always because you're missing some of the physics. In the case of kinematic problems to do simply with space and time, it's always to do with the three major physics effects: time dilation, length contraction, and the relativity of simultaneity. Paradoxes arise when you don't use all of those effects that actually apply